Chapter 24, Section 3, Photons. Light has both wave-like and particle-like properties. By particle-like, we mean that the energy of a light wave is divided up into little bundles called photons. Each atom that makes light gives off one photon at a time. Each atom that absorbs light absorbs one photon at a time. A beam of light consists of trillions of photons traveling at the speed of light. The photon theory of light. Photons. The energy of a light wave is divided up in tiny bundles called photons. Each photon has its own color no matter how you mix them up. Orange light is made of orange photons, red light of red photons, and so on. You can almost think of photons as colored jelly beans, except that they have no mass. This section says some things that are wrong. It is true, the lowest energy photons we can see are the ones that appear red to our eyes, as shown in figure 24.16, and the highest energy photons we can see are the color of deep violet. The next two sentences are very wrong. It's not low energy atoms, it's when an electron makes a small jump. Or when electrons don't have a very high temperature. It's not about atoms gaining and losing energy like that, so ignore those last two sentences. White light. White light is a mixture of photons with a range of energy. This is because white light is created by atoms that also have a range of energy. For example, when a dimmer switch is set very low, the filament of an incandescent light bulb is relatively cool and has low energy, so the light is red. As you turn up the switch, the filament gets hotter and makes more green and blue light. At full power, the filament is bright white, which means it is producing photons of all colors. What they mean by atoms that have a range of energy, they're talking about the temperature. This is not a very good way to explain it, but it has to do with the temperature making thermal radiation compared to atomic emission. Temperature and energy. The atoms in a material have a range of energy depending on temperature. At room temperature, or 20 degrees Celsius, a rock gives off no visible light. It's giving off infrared light. At 600 degrees Celsius, some atoms have enough energy to make red light. At 2600 Celsius, atoms can make all colors of light, which is why the hot filament of a light bulb appears white. The energy and intensity of light. Energy, color, and intensity. The intensity of light is a combination of both the number of photons and the energy per photons. There are two ways to make light of high intensity. One way is to have high energy photons. A second way is to have a lot of photons even if they are low energy, as shown in figure 24.17. In practical terms, to make a red light with an intensity of 100 watts per meter squared takes a lot more photons than it does to make the same intensity with blue light. Glow-in-the-dark plastic. If glow-in-the-dark plastic is exposed to light, it stores some energy and later is able to release the energy by giving off light. The plastic can only make light if it is charged up by absorbing energy from other sources of light. You can test this theory by holding your hand on some uncharged glow-in-the-dark plastic and then exposing it to a bright light. If you then bring the plastic into a dark area and remove your hand, you can see that the areas that were covered by your hand are dark while the rest of the plastic glows, as shown in figure 24.18. Photoluminescence. The glow-in-the-dark effect comes from phosphorus atoms that are in the plastic. When photons of light collide with the phosphorus atoms, the energy from the photons is stored in the atom. Slowly, the stored energy is released as pale green light. The process of releasing stored light energy is called photoluminescence. An experiment with photon energy. Glow-in-the-dark plastic demonstrates that a single atom only absorbs a single photon at a time. Let's say we want a phosphorus atom to give off a green photon. To give off green light, the atom must absorb equal or greater energy. If one red photon is absorbed, the atom does not get enough energy to make a green photon and cannot glow. However, if a single atom could absorb 2 or more red photons, it might get enough energy to emit a green photon. If you try the experiment, you find that even very, very bright red light does not make the atoms of phosphorus glow. However, even dim blue light causes the atoms to glow. This is because one blue photon has more than enough energy to allow a phosphorus atom to release a green photon. If you try different colors, you will find that only photons with more energy than those of green light will cause the glow-in-the-dark plastic to glow. Absorbing, reflecting, and creating light. Light reflects off surfaces. Light reflecting off a wall in a room started at a light source like a light bulb. Atoms in the wall first absorb and then re-emit the light energy. This process of absorbing and re-emitting light happens so fast that we may accurately describe the light as reflecting off the surfaces. The process of how light is reflected. The atoms on the surface of this paper, or screen, in the white area absorb the light from the room and immediately emit almost all of the light back in all directions. You see a white page because the atoms on the surface of the paper absorb and re-emit all of the colors equally, as shown in figure 24.19. The black letters are visible because light falling on the black ink is almost completely absorbed and no light is re-emitted. Most atoms absorb and emit light. Almost all atoms absorb and emit light. For most atoms, the absorption and emission of light happens in less than 1/1,000,000th of a second. This is so fast that only the most sensitive instruments can detect the time delay. However, a phosphorus atom in glow-in-the-dark plastic is different. Phosphorus atoms have a special ability to delay the emission of a photon for a relatively long time after they have absorbed light. Light from chemical reactions. Many chemical changes release energy. Some of the energy is absorbed within atoms and re-emitted as light. For example, the warm, flickering glow from a candle comes from trillions of atoms in the wick giving out photons as they combine with oxygen atoms in the air, as shown in figure 24.20. The light that comes from a glow stick is also made through chemical changes. The electromagnetic spectrum in the sky. For thousands of years, people have looked up at the sky and wondered what the sun, moon, and planets were made of, how they were created, and what kept them going. Did you know that they emit much more radiation than just visible light? Electromagnetic radiation has helped scientists learn more about our solar system, galaxies, and the universe around us. For example, astronomers confirm the existence of black holes, very dense objects in space that have huge gravitational fields, using X-ray telescopes. Visible light. The earliest observations were made using visible light because very little special equipment was required. The human eye makes a pretty good observation device, and with a telescope it's even better. Astronomers use telescopes to do more than just magnify images. For very dim or distant objects, very little light reaches Earth. Telescopes act as light buckets and collect as much light from a dim source as possible. Bigger telescopes can collect more light than smaller ones and allow scientists to see objects that are further away and dimmer. A different approach to getting better pictures of the sky in the past 50 years is to launch telescopes mounted on satellites into orbit beyond the atmosphere. These new telescopes, like the Hubble Space Telescope, can show us crystal clear views we could never obtain on Earth. Emission spectra. Another way in which scientists learn about celestial objects is by observing emitted light. Astronomers use spectrometers to determine which frequencies of electromagnetic radiation are present in light from stars. Patterns of spectral lines can be associated with chemical elements, so when a particular pattern appears in the spectrum of a light from a star, it's a good sign that element is present in the star. Radio telescopes. While performing a study on radio communications in the early 1900s, an engineer discovered an unknown source of interference. It turned out that the source of the radiation was located in the sky at the center of the Milky Way galaxy. To further investigate the sources of radio waves in space, scientists built radio telescopes. Because radio waves have a much longer wavelength than visible light, equipment used to accurately detect radio waves must be much bigger. The biggest radio telescope in the world is the Arecibo Radio Telescope in Puerto Rico. It's over 300 meters across and built into a huge sinkhole in the ground. In the 1960s, new theories predicted the existence of a certain kind of pulsing star, and astronomers found them by observing radio waves. Gamma rays and X-rays. Other objects in the sky emit high-energy electromagnetic radiation like X-rays and gamma rays. Unlike most visible light and lower energy radiation, high-energy electromagnetic waves do not usually pass through the atmosphere, so observations of this radiation are made from satellites. This image of the supernova remnant Cassiopeia A was taken by the NASA satellite Chandra. Infrared telescopes. Because water vapor in the atmosphere absorbs much of the infrared radiation coming from space, infrared telescopes are often built high in the mountains, like the Mauna Kea Observatory in Hawaii, which is about 4,000 meters above sea level. Scientists also mount infrared sensors on an airplane and fly above 99% of the atmospheric water vapor to take more sensitive readings than on the ground. While observing a star passing behind Uranus, they saw it blinking in and out of view, and it was discovered that Uranus has rings similar like Saturn. Astronomers learned that the surface of the moon was covered with a very fine powder years before anyone set foot there by making observations of reflected infrared light. Electromagnetic Variety Show. Below are 4 images of the Crowd Nebula. Clockwise, starting in the top left, the images were taken in the X-ray region of the spectrum, the optical range, which means visible light, with a radio telescope, and in the infrared spectrum.